Hello friends, welcome to our 14th lecture of the estimation and detection theory course. And in this particular lecture, we are going to look at the estimator-correlator. So let me do a quick recap of what we were doing in the last lecture. So now we were looking at the detection of random signals. So we were looking at the detection of random signals. What do we mean by random signals here? That the exact signal is not known, but the signal statistics are known. So we mean by this is that the signal statistics are known. Especially what we want we know is the PDF or the covariance. Okay, so we know some of these things about the signal. So given a particular PDF, for example, we were taking an example of a Gaussian random variable. So the random signal was generated using this distribution and then it was transmitted. At the receiver, we have to detect if such kind of a signal has been transmitted or not. So in the last class we took a very simple example of again a two hypothesis case, a binary hypothesis case where H0 was just the noise. The noise was a wide Gaussian noise with mean 0 and variance sigma square, and the alternate hypothesis was signal, which is Sn plus Wn, and we know that signal was again a Gaussian with mean 0 and variance sigma s square. Okay, so this is the example that we discussed last time, and we obtained energy detector from, so the best optimal detector in this case was a energy detector. So it meant that our test statistics T of x bar is equal to the summation I goes from 0 to capital N minus 1 of xi square. Okay, and if it is greater than lambda, some lambda dash, then we choose hypothesis H1 and so on. Okay, so this was our this is what we discussed in the last lecture. In this lecture we are going to move a little further and see what happens if this signal rather than having independent samples, the samples are correlated. Okay, so in this case we are going to look at a general Gaussian random process. Okay, again with mean 0, mean is 0, and variance now is given by a covariance matrix. Okay, so variance is given by a covariance matrix, and let us denote it by C of S. Okay, so let me again write the problem that is with us. So the null hypothesis is again Xn is equal to Wn. Wn's are wide Gaussian noise, again with mean 0, variance sigma square. I am writing I here just to show that the noise samples are uncorrelated. So uncorrelated noise samples, or I can write it to be a wide Gaussian noise. The hypothesis H1 is x of n is equal to Sn plus Wn, and now Sn is colored Gaussian process, and the distribution of Sn, let me write it as 0. Now 0 is a vector, and the covariance matrix is given by C of S. Okay, now we have this problem at hand, and let us try to detect it. So what we do is we form the NP test, we use the NP test method. So what is NP test? Again the likelihood ratio, this is equal to the probability of x given hypothesis H1 divided by probability of x given hypothesis H0. Now the probability of x given h0 hypothesis, this is fairly simple. It is just comprising of the noise, so I can directly write it as 2 pi sigma square power n by 2 times exponential of minus 1 over 2 sigma square summation xi square. I goes from 0 to capital N minus 1. Okay, please note here that my n goes from 0, 1 to capital N minus 1. Alright, so this is my likelihood for hypothesis H0. What is going to be the likelihood for hypothesis H1? This is, so you can see here, if you see this very closely, so x of n now follows. So let me write it here. So x of n is Sn plus Wn, and see, this is also Gaussian, this is also Gaussian, again with mean zeros. So the overall is distributed as a Gaussian with mean 0, and now variance is going to be added. So variance is Cs plus sigma square I now. Okay, so this is the overall variance of this xn under hypothesis H1. So in this case, let's write the likelihood function. So probability of x given H1 is equal to 1 over 2 pi power n by 2 determinant of, the determinant of Cs plus sigma square I power half. This is how we write for the Gaussian case with the correlated samples. Then it is minus half x transpose, x now I'm taking as a vector, x transpose times Cs plus sigma square I inverse x. Alright, so this is my likelihood under hypothesis H1. See, this one here I can also write it in vector form. So I can write summation xi square as x transpose x. Okay, let me also define what is x. X is a column vector. X is a column vector with elements x0. Sorry, I should not write like this. I should write x0, x1 till x of capital N minus 1. Alright, so I can write it in this fashion here. So okay, so this part I can replace it with x transpose x. Alright, so now let me take the likelihood also. Likelihood L of x is equal to 1 over 2 pi n by 2 sigma power n, sorry, this is going to be the determinant of Cs plus sigma square I power half. I is the identity matrix. Okay, let me write it also. I is the identity matrix. What is the dimension of this matrix? This matrix has dimension n cross n. Okay, because we are taking n samples here, so the matrix will become n cross n. Alright, exponential of minus half x transpose Cs plus sigma square I inverse x divided by the likelihood of the hypothesis H0, so 2 pi n by 2 sigma power n exponential of minus half x transpose x, and then there is also a sigma square also, so let me write it as 2 sigma square. All right, so we can see these two things cancel up. What we get is sigma power n divided by the determinant of Cs plus sigma square I power half. All right, exponential of minus half times I can write it as, so x transpose cs plus sigma square I times x minus 1 over sigma square x transpose x. Alright, so this is obviously greater than lambda, some value lambda for hypothesis H1 to be detected. Alright, so let me take this part to the other side and I take the log. Okay, this is a basic thing that we have been doing. So what we get on the right hand side is the log of lambda determinant of cs plus sigma square I power half divided by sigma power n. This is a log is greater than, I take the minus inside, so what I'm going to get is 1 over sigma square x transpose x minus, I'm going to take the 2 also to the other side, so it becomes 2. Okay, minus x transpose cs plus sigma square I, so sorry, this is inverse x. All right, and I can also write it in a more compact form. Let me take x transpose x common, so I can write this particular quantity as x transpose 1 over sigma square I, all right, times x. I can write it in this fashion, minus x transpose cs plus sigma square I inverse x is greater than, let me call it as lambda prime. All right, so what finally I get is that x transpose of 1 over sigma square times I minus cs plus sigma square times I inverse x is greater than lambda prime. All right, now there is a beautiful approximation that is done for this case. So this is not an approximation, so this is a using the matrix inversion lemma. So I'm just directly writing, I'm not going to show how it happens, but I'm going to directly write it. cs plus sigma square I inverse, I can write it is equal to 1 over sigma square times I minus 1 over sigma power 4 times 1 over sigma square I plus cs inverse. Okay, so I can replace this particular entity by this quantity here. So let's do that. So this becomes x transpose 1 over sigma square I minus, this becomes 1 over sigma square I plus 1 over sigma power 4 1 over sigma square I plus cs inverse x, right? And you can see these two things get cancelled. Now I'm going to do one last thing here. I'm going to write this identity as cs inverse. We know that a inverse is an identity, so I'm just going to replace this identity here with cs inverse. All right, so let's do that. So it becomes x transpose of 1 over sigma power 4, this is cs inverse, and I'm going to take 1 over sigma square also outside. All right, so I can take this 1 over sigma square outside, this becomes cs inverse plus cs inverse whole inverse times x is greater than lambda dash. All right, now what I can do is I can take the cs inverse, sorry, this will become, actually when you take sigma square outside you have to multiply it here with sigma square, so let me multiply it with sigma square, and let me take the cs inverse also outside. So let's do that. So this implies So this implies x transpose of 1 over sigma power 4. Let me do it something like this. So this becomes, so CS inverse I am taking outside, so what I am left with is CS plus sigma square I, alright, over sigma square times CS inverse whole inverse x is greater than lambda prime. Alright, now this sigma square is a constant, I can take it outside. Here there is a power of -1, so I can take this sigma square, it will come in the numerator. So the first thing that we note here is it becomes 1 over sigma square, and then inside you can see if I take inverse, so these two are matrices, so A into B whole inverse is B inverse times A inverse, right? So again using the same strategy here, so what I'm going to get is I'm going to get CS times CS plus sigma square I inverse x is greater than lambda dash. 1 over sigma square is a constant, I can take it outside and it could be merged with lambda dash here. Alright, so what I'm going to be left with is x transpose CS plus sigma square. So sorry, this is going to be, yeah, this is okay. Yeah, so sigma square I inverse of x is is greater than lambda dash, and this is what we get as our final test statistic. Okay, so this I can write it as my test statistic here. This is my Tx, and let me do one more thing here. Let me write this particular entity here as, say, S hat vector. So S hat vector, let me define it as CS times CS plus sigma square I inverse x. So my test statistics Tx will become x transpose S hat, or in other words I can write it as a summation over I goes from 0 to capital N minus 1 x of I S hat of I, and obviously this has to be greater than some lambda dash to detect hypothesis H1 to be correct. Alright, now you can see this particular quantity here, and this is called as the estimator for x. Alright, this is called as the estimator for x. Why it is called an estimator for x? If you remember in our estimation theory, if you remember, recall from estimation theory, so if you had some signal x of n which is equal to s of n plus w of n, and we are given Sn to be a Gaussian with mean 0 variance CS, and obviously the noise is Gaussian, mean 0 variance sigma square I. Then we know that we will use a Bayesian estimate. So we want to estimate S of n using the observations x of n. So we will use the Bayesian estimate. And what is the commonly used Bayesian estimate in this case is the MMSE. Okay, this was the minimum mean square error estimate. Okay, and if you recall from there, for this kind of a MMSE estimate, we could give the S hat of n to be equal to the correlation. So let me talk in the vector form. S hat is the correlation between S and and x, here the observation is x, times the covariance inverse of the output times the output. Okay, if you recall, this is what we derived for the MMSE estimator. And if you solve this further, so covariance of s into x is the expectation of s vector times s plus w vector. S is our real vector transpose, and the x is the expectation of s plus w times s plus w transpose, and then taking the inverse of this expectation times x. And if you see, I can open this bracket, so this becomes, the first part becomes expectation of s transpose plus expectation of s w transpose times the expectation, so I have to take an inverse of this expectation, and there will be 4 terms here, s transpose plus expectation of s w transpose plus expectation of w s transpose plus expectation of w transpose. And you can see here the s and w are independent of each other, so this will go to 0. I can write this in terms of expectation of s times expectation of w, and expectation of w is 0 because the noise is 0 mean, even the signal is also 0 mean, so this goes to 0, this also part goes to 0, this part also goes to 0. By definition, this is our covariance, which is cs. Again, this is cs, and this is our covariance of noise. So overall we get cs times cs plus sigma square I inverse x to be our estimate of s hat here. All right, so the test statistics that we get here is, what it says is that what we are doing is that we are correlating our estimated value with the observed values. Okay, so I can draw the diagram for this case. So let me draw the diagram for this case to show you how it comes out. So tx is, in our case, is x transpose at s hat. S hat is again the estimator of the signal, and what you are going to do is you are going to take your input x of n. First you are going to estimate s hat. You are going to get the s hat by multiplying it, or by multiplying it with cs times cs plus sigma square I inverse. All right, so you get here s hat of n, and then you multiply these two quantities together, and then what you do is you sum it over from n0 to capital N minus 1. Here you get your test statistics, and then you pass it through the decision making block. Okay, so we took as lambda dash, so you can take it as lambda dash. So this will give you hypothesis h1, this is going to give you hypothesis h of 0. And this particular entity, this is also called as, such kind of a filter is also called as a Wiener filter. Okay, sorry, this is called as a Wiener filter. So this is called as estimator-correlator. This is called as estimator-correlator. Why it is called estimator-correlator? Because what we are doing is we are first estimating the signal, and then we are correlating this estimated signal with the input. Okay, and then we are making the decision. Alright, so such kind of detector is called as an estimator-correlator for the detection of Gaussian random signal in white Gaussian noise. Alright, now you can also how to get these lambdas, you can again find out the distribution of t of x. Now t of x is again going to be a Gaussian random variable. With now will be the mean will shift. Obviously, it is, you can see it is a x square form. So if you see this t of x here, so t of x here, you can see it is to be a x square or a quadratic form. So it is again going to be a Gaussian square. So it is going to be a chi-square distribution with certain variances and certain parameters changed. So you can think of it to be a chi-square distribution again with the degrees of freedom n. Okay, so we are not going to go into those details now, but what I'm going to show you is that if we take a very simple case as we took for the last time. So suppose if your S of n is a normal Gaussian, okay, a Gaussian with mean 0 and variance sigma s square I. So I'm talking about the white Gaussian process. Then the test statistics t of x is x transpose cs plus sigma square I inverse times x greater than lambda dash. How this changes? So I can replace this cs with sigma s square I. So let's do that. So the tx will become in this case is x transpose sigma s square plus sigma square. Obviously there will be a I component inverse x, and you can see here I inverse, this is a constant, so it will go into the denominator. I inverse times I will become again identity. So this turns out to be sigma s square over sigma s square plus sigma square times x transpose x. All right, and this is a constant, so you can take it to the other side, and this x transpose x is what? Summation xi square is greater than lambda double dash, and this is what we got as our energy detector in our previous case. All right, so so we can see that using this estimator-correlator we can detect the signal in case when the signal is a Gaussian random variable with some covariance matrix. All right, I will stop here for this class. In the next class we will take from here and see another form of drawing this estimator-correlator and see some more examples. Thank you very much.